Hello, and this is the fourth video in this series of videos about random number generators that accompany the book, Random Number Generators, Principles and Practices. And it's the second one on entropy sources, which is where you get the non-deterministic data that can then be turned into random numbers. So in this one, we're going to look at metastable sources. Now, what is metastability? If you're a hardware engineer or digital engineer, you almost certainly do understand what metastability is. But I'll give a little explanation. There's a good human analog. If you imagine that you're walking down a corridor and somebody's coming at you, and you're going to have to step out of the way. And so you step to the left, but they step to their right? So your left. You both move in the same direction. You think, oh no, and you step in the other direction, but the other person does it at exactly the same time for exactly the same amount of distance, and then you go back and forth and back and forth. But as soon as there is a bit of timing difference where somebody first steps in one direction and you see them do that, then you step in the other direction, and then you pass. And so that state of flipping back and forth, left and right, until there's a difference so you can pass, is a metastable state. It is theoretically going to go on forever, but sooner or later a little bit of difference will lead to it being resolved, and you can pass. So that's a metastable event. In electronics, in say a digital flip-flop which stores 1 bit, when there's a clock and an input, and the data on the output of the flop changes to what is on the input when the clock edge goes positive from 0 to 1. But there is some timing requirement that says, the input must be stable before the clock and after the clock for a little bit of time for that to happen. If they both transition at the same time, is it going to see the 0 or the 1? Because it's gone from 0 to 1, is the flip-flop going to, which one is it going to pick? And if you're not meeting the timing requirements, it could end up as either, or it could go metastable for a period where it kind of hovers around in the middle until a bit of electrical noise causes it to flip one way or the other. And this is an inevitable thing in digital electronics, where if there are asynchronous systems with different clocks that aren't related to each other, the data trying to get from one of those domains to the other is going to go metastable at some point with some probability. So in this talk, we're going to look at 2 metastable sources. One is the forced latch, and one is a metastable ring oscillator. And actually 2 types of metastable ring oscillator we're going to look at. They're quite similar, but a bit different. Then after this talk, there'll be 3 more kinds of entropy sources we'll look at. And that pretty much covers all of them in general. Right? If you look at any entropy source, they fall into one of these categories, usually. Okay, so let's think about this corridor or flip-flop metastability problem. You can think of it like a ball falling on a hill. So here we have a ball, we're dropping it on a hill, and if it goes to the right, we're going to get a 1. If it goes to the left, we're going to get a 0, a digital 1 or a digital 0, and that will be our random bit. And we'll keep repeating that. But if this is perfectly symmetric, there's no noise, everything's stable, it could just land on the hill and stay there, right? Not go left or right. It's perfectly balanced. And we can think of this as, you put a ball on the top of the hill, and it might stay there for a while. But any bit of disturbance, a bit of wind, or a tiny earthquake or something, vibration, would cause the ball to shift a little bit to the left or the right, and then it would keep on going. And so it would be the noise of that interference of vibration or whatever leading to it determining whether it goes left or right. However, if the ball is being dropped to the right of the top of the hill, it's always going to go to a 1. And if it's falling to the left of the hill, the top of the hill, it's always going to go to a 0, very reliably. Now, if this thing is moving around, there's some noise in its position, maybe that noise is big enough to get it over to the other side of the hill sometimes, and then part of the time it'll go left and part of the time it'll go right. Now, the reason we're doing this this kind of model is because it very accurately represents how the electrical circuit works of a metastable entropy source. So it's got a couple of parameters here. So let's think of the ball moving left and right, and that its position in time is normally distributed. So anytime you drop it on the hill, its average position is near the top of the hill, but it could be somewhere to the left and somewhere to the right. And we have a standard deviation for that position that we call sigma n, which is the dynamic noise of that ball in terms of its position left or right. Then we've got the hill itself, which could be in the middle, it could be on the left, it could be on the right. Its position, again, is normally distributed, and we call that sigma m. So the n is for noise, and the m is for manufacturing noise. So in a digital circuit on a chip, that manufacturing noise is all the variation of dopant atoms and layer thickness and things that vary when you manufacture silicon. There's always some variation. And in fact, the smaller the device is, the greater the variation. You think of one atom being here or there, creating a difference. As the device gets smaller, it's made of fewer and fewer atoms. That one atom has a bigger and bigger influence. So in today's silicon, we try to use the smallest devices for random number sources so that we get the most manufacturing noise. And why is that? Well, if sigma n, the noise of the position, is much greater than sigma m, then we end up with a random number generator, because that noise on the top here, this ball position, is dominating the noise of the hill position. Now, the hill position is stuck in position. It varies over many chips. You might build 1 million chips, and if you look at the position of the hill, or what we might call the bias in the circuit, according to across all those devices, it's going to be distributed normally. But if you build a single chip, it's just going to be one of those positions, and it's going to stay there because the atoms you dropped down to make the transistors, they're going to remain in place. Well, usually, right? There's some degradation over the lifetime of the device, but more or less that bias remains. So as long as this ball is moving left or right much more than the possible different positions of the hill, then the rightmost position of the ball will be on one side and the leftmost position of the ball will be on another side of the hill. And so the outcome will depend of the bits we're getting out of this process are going to depend on the noise driving the ball. Now, there's another kind of circuit called the physically unclonable function, which will be a whole other set of videos after the random number generator videos. And this is what we consider a kind of a static random number that a circuit generates. It always produces the same one, but but the circuit, when you build it, you don't know what number it's going to produce. So if you build it in multiple different chips, you get a different random number. And if they have enough bits in those random numbers, they are always going to be different. They're always going the number you get, say a 256-bit number from 256 puff cells, is going to be a different number, because the probability of all 256 bits being the same on any device is very, very small. Now, if sigma n is much smaller than sigma n, so this hill could be moving from over a wide range of positions, but the ball is pretty much staying in place. It's not vibrating. It's not vibrating very much at all. Then the position of the hill is going to determine whether you get a 1 or a 0, and that's always the same position in the same bit of silicon. And so you'll get a random number as a function of a random bit as a function of what the bias in the circuit or the position of the hill ended up being, but and you could turn the circuit on and off and on and off, and it would always produce the same bit, and that's what we'd call a physically unclonable function. And I won't go into more on puffs, that's for a later thing, but we have these requirements. And how much of a requirement? Generally, you want sigma n to be at least 10 times bigger than sigma m. And for a puff, you want the reverse. You want sigma m to be at least 10 times bigger than sigma n. Now, so one proviso here is when you build a circuit with, say, a cross-coupled latch, which we use for a flip-flop, it's not true that sigma n is 10 times bigger than sigma m. It's usually 2, 3, 4, 5 times bigger, but it's not 10. And that's a problem, right? Because you build this circuit and it's not noisy enough to give you a random result. You'll probably get a very biased result, or always get the same result. It lands somewhere in between an RNG and a puff. Okay, so here's an example of a working type of random or entropy source based on metastability. So here's the basic circuit: 2 NOT gates back to back. So whatever bit 0 or 1 you get on the input, you get the inverse bit 1 or 0 on the output, and vice versa. So you can imagine if this node A is a 0 coming out of here and going in here, you get a 1 coming out of here and going into here, so you get a 0 coming out. So this is a stable configuration. It holds itself with a 0 here and a 1 here. Now, if I were to force both node A and node B to, say, a 1 by attaching some honking big transistors to node A and node B and turning them on so they're both pulled to the same value, and then I turn those transistors off and let the circuit decide whether it's going to be a 1, 0 or a 0, 1. If everything is equally balanced, if these two buffers have the same strength, electrical strength, then the noise is going to determine the outcome. So each time you turn it off and turn it on, or pull the sides down or up, and then release it, then it will the noise will determine whether it becomes a 1, 0 or 0, 1 state, and therefore you get a random bit. So here in this circuit, we have this cross-couple latch that is up here, but with a bunch of stuff around it. And this is what is implemented in the random number generator in Intel chips. This is kind of a cartoon version of it. For instance, if you were to dig into one of these transistors, you would find many transistors stacked, because these are supposed to be very weak. So we make them weaker by stacking them, so the resistance goes up. And down here are the honking big transistors, which pull it down. So when this line asserts, it pulls both sides of this cross-coupled latch down to close to 0 volts. And we see these two buffers. It sees 0, 0. And when you release it, what we'll see is, let me go to this diagram here. When a circuit goes metastable in silicon, now it's possible to have metastability where the state of it is flip-flopping between a 1 and a 0 or 1 and a 0 until it gets till it decides to go one way or the other. That's not what happens in silicon. You get some current through both legs of the circuit, and it kind of hangs around in the middle until some noise kicks it to go one way or the other. And the length of time it persists in this metastable state is an exponentially decreasing function, right? So the probability of it diverging early here, so the circuit is powered on, both ramp up together as the voltage is increasing, and then some noise causes them to start diverging. So this ramp here is actually the power on ramp of the circuit, and at some point it starts diverging. But it might stick in the metastable state for a period of time, and the chances of it starting to diverge, or the chances of it not having diverged by some time, exponentially decreases with time. So this bit here, where it's hanging around in the middle for some extended period, is much less likely than this happening here. So if we go back to this, we have these two buffers, and what they're seeing is a 0, 0 because we pull down both sides, and then we've released them and they start to move up. But they end up seeing they're still seeing a 0, 0 until one or the other diverges, right? Until they diverge, at which point one of these will become a 1 and one of these will become a 0, or this will become a 0 and this will become a 1. And this buffer is labeled as high skew. So What does that mean? That means, go back to this, go back to this. The threshold for that buffer seeing a 0 or 1 is not in the middle. It's up here somewhere. So as both the halves of the circuit, this red is representing one half of the circuit and the blue the other half, if both of these are in the middle and the threshold for the buffer to see a 1 is above it, then it's going to see a 0 and a 0. So it'll output a 1 and a 1. But at some point it will output a 1, it'll diverge and it'll get a 1 and a 0, and this will lead to a pulse being made here, which goes through a little delay, and it goes around here, and that pulse then pulses these clocks again and causes the process to repeat. So this loop around here, once the resolution is detected, as in we get a 0 and a 1 or a 1 and a 0, not a 0 and a 0, the circuit then pulls both sides back down again, and the process starts. There's a big loop, and this circuit self-oscillates. But we've got another feedback path. In fact, we've got two of them, so they're symmetric. And here is a one-shot. This creates a pulse as the circuit flips. And the pulse is either on this side, because there's the one here, or it's on this side because this became a 1. Right? So if it's a 0, this pulse doesn't happen. If this is a 0, this pulse doesn't happen, and this one does happen. So let's say we have the pulse on this side. It will come through here, and it will turn on this transistor, which will pull some charge off this capacitor. It will also carry on around here and turn this on this transistor, which will push some charge onto this capacitor. If this one fires instead, it will pull some charge off this capacitor and put some charge on this capacitor. So the two capacitors are they're somewhere in the middle, but if you get a number of 1s out of the circuit, it'll push the capacitors apart from each other in a direction which will weaken the side which is producing the 1s, or the stronger side, and so it and then moves back again. If you get more 0s than 1s, it starts going in the other direction, pushing it to create more 1s. And so you've got this stabilizing thing that if you're getting too many 1s or 0s, it starts to produce more of the other value. And that, in effect, is pulling this hill into the middle. So we've got some manufacturing bias, and we're applying this load on the capacitors, a voltage, to load the circuit on one side or the other, to move the hill into the middle. And so we end up with this situation where the manufacturing noise is maximized because we're using, the thermal noise is maximized because we're using small transistors, but the manufacturing noise, the position of the hill, is being compensated for with this feedback network that's trying to put the hill in the middle, and so sigma m is smaller than sigma n. So that is the basic circuit we use in Intel chips to produce entropic bits. So we take the output and out it goes downstream to the rest of the circuit. So that's an entropy source. Now there's a paper. This is by a colleague of mine called Rachel Parker. Entropy justification for metastability-based non-deterministic random bit generators. And in this paper, Rachel makes a model of this entropy source. And what we have here is a Markov chain with a set of probabilities. And what the Markov chain is representing is where are we on the metastability curve. With this, you can think of this curve representing the probability of moving away from the middle. So as you go out to the left, you're less and less probable to keep on going out to the left. You're more likely to move to the middle, and vice versa on the other side. And so it's a mathematical model. The probabilities in this Markov chain represent this curve. And so that's the feedback network. The steps we're putting on the entropy, on the capacitors, is moving you over this hill, but you're being pushed towards the middle. There are a couple of possible outputs that are the most likely output. For instance, you're sitting on the left, you're more likely to move to the middle, but you hop over, you're symmetrically about the middle of the curve, and so you go to this state, or so you're here and you go here and back and forth and back and forth, and so you're creating a 1 0 1 0 pattern. Or you might be not centrally about the middle. It might be that you have a state bang on the middle, on the top of the hill, and one off to the side. So you'd go this, and then you might equally go left or right, but then you get to this state, and you most likely go back to the middle. So you're going from the middle to one of these two, back to the middle. Now, if we call a left move a 1 and a right move a 0, this positioning of the feedback steps around the hill is going to lead to a most likely symbol coming out, or pattern coming out of 1 0 1 0 1 0 continuously, just because that's the most likely set of probabilities. Any other walk around this hill will be less likely, because when you multiply together all the probabilities, you end up with a smaller amount, because these probabilities are smaller. However, when you follow this for an infinitely long Markov chain, you just say, what's the most probable symbol of an infinite chain of outputs from this random number source? You find that the probability of the 1 0 1 0 pattern, or a 1 1 0 0 pattern that you might get out of this, or any of the other patterns that you can get that are the most likely pattern, they're all equiprobable. The chances of getting those patterns is identical when you do the Markov sum. And you do some more math, and you find out that the min entropy of the pattern coming out of a set of bits is strictly a function of the step size. So that's how much, in the case of the circuit, how much entropy are we moving, how much voltage are we moving the capacitors by? We find that the entropy is a function of that step size divided by the noise on the thermal noise, the input referred thermal noise, if you know what how analog electronics works. And this phi is the normal cumulative distribution function, and then negative log 2. We'll get to that, but in the definitions of entropy. But here, this says you've got some noise in your circuit. You can't do much about that other than use small devices, but you can choose what your step size is, and the lower the step size, the higher the entropy. So that's quite nice. This is a result that's independent of any other properties of the circuit. It's that it says you need your feedback step size to be small and your thermal noise to be large, and then you'll have high entropy. So that's a pretty good result. And what it tells us is a feedback-controlled metastable circuit makes an entropy source which you can predict the entropy for based on the step size of your feedback circuit. Okay, so we're going to now look at this is one that was by a paper which right, yeah, okay. So this is one that was designed for FPGAs. So field programmable gate array. So this is a chip which has a set of programmable logic elements and programmable interconnects, and you can design digital logic and put it on those chips. They tend to be big and expensive compared to custom silicon because they're programmable, but they're very useful for being able to design circuits which you either don't need a lot of because you're not built, so you don't want to build custom silicon, or you want to reconfigure. So there's a problem there that you don't get to build analog circuits like the one I just described. So like this one, you don't get to build that circuit in an FPGA. You only have digital functions like flip-flops and logic gates. So so what they've done is they have taken an RS flip-flop where you would have a NOR or a NAND and a feedback path, and that would be a flop which, when you put a 1 on one of the inputs and a 0 on the other, and return both inputs to 0, 0, the output will have switched, so one of the outputs is a 1 and the other is a 0, and it'll stay there. And when you raise the other input to be a 1 and drop it back to a 0, the output will flip, so the other bit is a 1 or a 0. And the change they've made is to put an exclusive OR in instead of a NAND or a NOR gate. And so what happens is, each time one of the inputs to these XORs changes, the output changes. So you get a pulse which is moving around the circuit and keeps moving around and around the circuit. And so here is the control input wire moving up, and you get a period of oscillation here. This is the voltage oscillating up and down until it ends up high. It finishes high, and then the control input wire goes low, and it starts oscillating again until it lands low. So it's like an RS flip-flop, but a really bad one that goes metastable and then resolves every time you invoke it. What we have at the end is a toggle flip-flop. So this is a flip-flop which every time you clock it, it just inverts the output. So it's outputting a 1, you clock it, it'll output a 0, and if it's outputting a 0, you clock it, it'll output a 1. So what that's doing is counting the number of oscillations. You start at say 0, the state of the toggle flip-flop, and then you have a number of oscillations. If you have an odd number of oscillations, you'll get a different output to if you have an even number of oscillations. And that's where the randomness is coming from. The noise is determining the resolution time, so it's determining the number of oscillations, and so you get a random bit out. This here is what you'd get on the plot of an oscilloscope. If you looked at the output with a persistent trace, where you're seeing the superposition of multiple bits out from this, and you see it's both high and low. You're getting bits out high and bits out that are low, and at the start, while the circuit is oscillating, it's changing its mind. It's oscillating too, flip-flopping up and down, but then it rests either high or low, and both happen. And then that value is captured and used. Now what's happening with those pulses, it starts off with these pulses going around and around the circuit, and you see they're getting thinner and thinner and thinner, these pulses, until they're sufficiently thin that they disappear. So because there's nothing keeping these pulses stable, there's some noise is causing those pulses to lose timing and become thinner. So that's a quite neat design because it's built with multiple digital components, not with any analog components. So you can build that in an FPGA. And this is when you test the output of this circuit, you find it's quite random. It has quite high entropy. Now, working out how much entropy is a challenge. All you can do is look at the output and measure it. We don't have a good model for determining mathematically how much entropy is there, but it doesn't matter. It's pretty high entropy, and we can measure it and then put in some margin and know we're good. So the next one I'm going to look at is a metastable ring oscillator. We talked about ring oscillators in the previous video, and I basically gave a bunch of reasons for not using them, because they're unreliable in many ways, and you have to do some significant engineering to know that you have got rid of all the problems that you might have. But so here I've said let's do a simplified picture of a ring oscillator. So we have in this one we have 17 gates, and I've plotted a gate that is outputting a 0 as a black triangle, and a gate that's outputting a 1 is a white triangle. So a black triangle is outputting a 1, and then you get a 0, and then you get a 1, and then you get a 0, and so on around the loop. And because there's an odd number of gates, you will always find there's a point where you're outputting a 1 into a gate that's outputting a 1. And so this gate here is going to transition from a 0 to a 1, from a 1 to a 0, because it's received a 1 on its input. And at that point where we've got this discontinuity, I've plotted it with a red dot. And when this gate changes, this red dot moves to the right to this one, because now this is outputting a 0 into this gate, which is outputting a 0, so it's going to flip. So this red ball is moving around the circuit, just circling around the circuit. And down here, what we have is 3 of these ring oscillators, and I've made them different lengths, and I've made them a prime number of gates, so that there should be a fairly large, or there shouldn't be any close integer ratios that these can lock to. Now, if you build the circuit for real, you're going to want to do some fairly deep electrical analysis to make sure the locking modes are at frequencies where these things can't run. But let's assume that this is a healthy set of ring sizes, and these things are oscillating at different frequencies on their own. They've each got one discontinuity. You can't have 2 discontinuities because that doesn't add up, but you could have 3 or 5, right? You could have any number of discontinuities in this ring up to the number of gates, but when 2 discontinuities collide, they cancel out, and so very quickly you end up with one discontinuity flowing around in these 3 loops. But this set of multiplexers here, when the control wire is flipped, instead of having 3 separate entropy sources, you have one big loop. So the output of one loop goes into the input of the other loop, and the output of this goes into the other one, and so on. And so you have one big loop, but you have one big loop which has 3 discontinuities. And so if you were to plot a point on this circuit, this one loop, you would see it operating at 3 times the frequency that you would expect it to run at, because it's got 3 discontinuities, so it's flipping up and down 3 times faster than you'd expect. But sooner or later, those discontinuities are going to bump into each other, because the noise is determining the time it takes to get from one side of a gate to the other. There's some fixed time plus a bit of noise, and what we know from these circuits is they collide very quickly. And that's partly because the activity in the circuit is creating some of the noise, so it's sort of depressing the speed of the one ahead and causing them to of a discontinuity close ahead and through the power supply, and so they collide very quickly. And you can think of this as an oscillator that's operating at a multiple of its basic frequency, but it wants to oscillate at its lowest fundamental frequency, but usually there's some forcing function causing it to oscillate at a higher frequency. And here we don't have that forcing function. It's going to resolve to just having the one discontinuity. And so it has a metastable state, which is 3 discontinuities running around the circuit until that state resolves to just having one. And the time it takes is driven, for that resolution, is driven by the noise. So again, this is a circuit which is built only out of digital components. So I invented this circuit, and I there's a section on it in the book. And so the goal here was to take something which is bad, which is a ring oscillator entropy source, and turn it into something good, which is a metastable ring oscillator or metastable entropy source. Because metastable entropy sources are good, but the ones we build in Intel chips are basically analog circuits with a lot of custom design, and that's fine for that purpose. But maybe we want to do this in a chip where we don't have the luxury of time or engineering time to do that. but we want to build something out of digital components that's still going to be reliable because it's metastable. And this is an example of that, and the earlier one was an example of that. So metastable ring oscillators are very good. Okay, so that was the point at which my computer ran out of power and turned off. So I'm back again now with it a bit more charge in there to finish up. So here it is. Here's the same circuit in the configuration where the multiplexers are setting it to one big loop. And when you tap one of the positions, like this position here, and you've toggled the control wire so it's little loops, and so that what you're seeing here is the output of this top loop in this mode, because you're tapping the output of part of that loop. But then when you turn the control so it's one big loop, the whole thing starts oscillating about 3 times slower, because it's a 3 times bigger loop approximately, and the phase of the resulting oscillation is a result of how the noise drove the circuit to revert to a single oscillating discontinuity. And so that phase varies. So you drop the control and then you sample whether you have a high or a low at that point, and that's your random bit, because the metastable collapse of the state of the higher frequency oscillation down to the lower frequency oscillation is driven by noise, and so the phase of the oscillation will be random. So that's the metastable ring oscillator. If you Google the metastable ring oscillator, you'll also find another paper written by some engineers at Samsung with a circuit which is similar in some ways and different in some ways. Instead of having a big loop, they have basically a single inverter, which is either fed back on itself or connected in a big loop. So it's as if this loop here was just a single gate fed back on itself, and then they have many more of them, right? They might have 15 or 31 or something in a chain of these single inverters. Going back to let me get the right slide. Back to this circuit. When you are in the fed back state, the single flop will be in the middle here. It'll just stay in the middle, because it's basically trying to feed back going 1 0 1 0, but it's going so fast that it just stays in the middle. There isn't enough edge time to get you to the edge. And then when you release it, it goes to one of these states. And so when you flip the control and turn it into one big loop, now you have a discontinuity on average on on half the bits. And they collapse into a single oscillating state, and again you sample it, and the phase is the resulting the phase is the resulting random bit. So it looks somewhat similar to this, except this this up down here, this oscillation here, is actually just a voltage in the middle, and then it goes to a known to a lower frequency oscillation, where the phase is what contains the randomness. So that's basically a basic look at metastable entropy sources. They are generally the most reliable kind of entropy source, because metastability is guaranteed to happen in asynchronous systems, in digital systems, and where you have any level of asynchrony and you're trying to sample data from one clock domain to another, it's going to happen. And here we're creating 3 clock domains and turning it into one. In the forced latch metastable resolver, we're forcing the single latch into metastability and letting the noise determine how it resolves, which is a fundamentally different structure. But that covers these things cover most of the types of metastable sources, with the added benefit that there is a lot of understanding of metastability and mathematical models that we can use to exactly predict the entropy that comes out of one of these things. And then that means we don't just have a circuit which appears to be random. We have a theoretical model that tells us how random it is. And when we build these circuits, we find that the mathematical description predicts a certain amount of entropy, the simulation predicts a certain amount of entropy, and when you build it, you get that same amount of entropy very closely. So you have the three models, the physical model, the simulation model, and the mathematical model, all agreeing. So this is another thing that makes random number entropy sources based on metastability to be very good sources, because they're both reliable, because you can rely on metastability existing, and they are well modeled. So that's the end of this talk, and you can look forward in the next talk to sampling noise. So this will be various forms of just taking noise from the environment and sampling it and trying to turn it into bits. So I'll see you next time. Thank you.